According to Wien's displacement law, as temperature increases, peak wavelength decreases. So what if we increase the temperature of a material until its peak wavelength is smaller than the smallest possible distance? Alright, every material in the entire universe emits light all the time. So you might think that for a material to emit light, it must be extremely hot, but that is not quite true. For even ice emits light, and your body emits about 100 watts of power as infrared radiation that we cannot see. But for a material to start emitting visible light, it must be heated past a certain temperature called Draper point, at which it starts glowing a dim red. So as you might already be thinking, light is of 7 types, and if we name them in order of increasing wavelength or decreasing frequency, then we have gamma rays, X-rays, ultraviolet light, visible light, which is the one we see, infrared light, microwave radiation, and radio waves. They are all made up of perpendicular electric and magnetic field oscillations, and they travel at, well, the speed of light. These lights, or more scientifically, the electromagnetic radiations, are all produced by different methods. For infrared radiation, any material that is not at absolute zero still has some energy, and this energy causes the atoms of the material to have some thermal motion. This motion emits light in the infrared range. Visible light is produced when the electrons of the atoms of a material are excited by heat or electricity into higher unstable energy levels. As they fall back to their original energy level, they release that excess energy as visible light. This is not a physical fall, but a fall from higher energy to lower energy, or when the material is just hot enough to produce visible light. So as the temperature of an object increases, its peak wavelength, the wavelength of light the object releases the most, decreases. So the object starts by emitting infrared light, then moves into visible light, and then towards gamma rays. This is called Wien's displacement law. The electromagnetic radiations are all forms of energy, and if we name them in order of how much energy they contain, then we will start from radio waves, move towards visible light, and then move towards gamma rays. So gamma rays are the most energetic of them all, and they are produced by extremely hot and energetic processes. To clarify this, as the temperature of an object increases, the object doesn't stop producing infrared light, nor does it produce less of it. Instead, it produces more of infrared light and of all the lights, just that its peak wavelength reduces and shifts towards gamma rays. The total energy that the object releases across the whole EM spectrum increases, and you can see this as the object brightens up. This is called Stefan-Boltzmann law. According to Wien's displacement law, as temperature increases, peak wavelength decreases. So what if we increase the temperature of a material until its peak wavelength is smaller than the smallest possible distance? Well, the smallest possible distance is called Planck's length, and it is equal to, and since there is no limit to the amount of energy that you can give a material, you would hypothetically need to heat the material to the Planck's temperature, which is, at this temperature, our current understanding of physics breaks down. But theoretically, if you compress a single photon's wavelength down to the Planck's length, the photon becomes packed with a staggering amount of energy. And Einstein's theory of general relativity tells us that energy equals mass times the speed of light squared, and this creates gravity. So a single photon with that much energy in it has a relativistic mass so large that its gravitational radius, its Schwarzschild radius, becomes equal to its wavelength, which is a Planck length. The moment this photon is released, it instantly collapses under its own gravity and forms a microscopic black hole called a cool goblet that traps the photon. But recent research suggests that the universe might have some quantum tricks to prevent this from happening. But here is something cool. Stars that are super hot with their peak wavelength in ultraviolet light look blue. Because we cannot see UV, but blue visible light is the one that is produced the most and closest to it. So when it is dark, just remember that your body is glowing with infrared light, but you cannot see it. Night vision cameras use this invisible infrared light to make you see in the dark. The subscribe button is emitting visible light for you to click. Thanks for watching.